So we'll begin the ladder problem. My understanding about the ladder problem is that we are to find the minimum coefficient of friction that will allow the person to stand at this point on the ladder and have the ladder not slide out from under them, correct? So we're looking for mu. I believe we can use a person mass M, climbs a ladder of length L, and the ladder has a mass M that makes an angle theta with the ground and touches a wall. There's no friction between the wall and the ladder. There's a coefficient of static friction of mu between the... That's not how you spell ladder. That's just silly. That's ladder. That means the second thing in a list. So spell check failed me there, didn't it? But I bet a second reading wouldn't have failed me. Mr. Shelton's just terrible about editing, apparently. But you guys already know that. So you know I'm terrible about editing. I should be better. You should expect more from your teachers. Speaking of which, let's do the net force part of the problem first. That seemed like a good place to start. All right, so the net force of the part of the problem first. I think we'll start here that there is a upward force, normal force from the ground on the ladder here. And there is a frictional force on the ladder here. And there is a weight of the ladder here. And there is weight of the person here. And normal force from the wall there. All good? Okay. Truthfully, the way we're doing the problem is correct, except these are the forces as they act on the ladder. Understand, this does not tell us what is safe for the person. Okay, the forces acting on the person are different and are at a different angle. Them falling off the ladder will be due to them being above the ladder with their center of mass here. Everyone understand? So this will tell us about the capacity of the ladder to have enough friction to hold it in place, but not whether the person should actually stand there. Not to mention, it is possible with them leaning backwards that they apply a different torque to the ladder, especially if they're holding on here. Everybody understand? So there are things about this that have to do with the center of mass of the system I am neglecting. But what we're doing when it comes to the forces acting on the ladder is all true and reasonable. Okay? And this will give us the answer we're looking for. All right. We should label them all so we have something. So normal from the ground, normal from the wall, mg and little mg, and friction, static friction. All good? So let's do the net force equals 0 problem, starting with the x direction and net force in the y direction, both equal to 0. I'm going to make this the y direction and this the x direction. So I get static friction equals normal force from the wall. Any question about that? And I get normal force from the ground equals mg plus mg. That all good? So then I will say the static friction has to be less than or equal to mu times the normal force from the ground. Right, these are all the things we did first semester, nothing new yet. So doing some subbing into this, I'll get normal force from the wall has to be less than or equal to mu times mg plus mg, or mu g m plus m. All that good? Any question about any of those choices that we've made? All right, so we have a torque problem to take care of next. But before we go to do that torque problem, let's handle something real quick. It's clear, and hopefully it's clear to you, that this is theta as presented in the problem. This is also theta, but this is 90 minus theta. So is this, and so is this. So we have two different angles. They're related, but we have two different angles. I was told by people in sixth period that some of you did not know that sine of 90 minus theta equals cosine theta. Is there anybody here who doesn't know this? Okay, so we all know this. Are we sure? So you would have known to do that substitution? If not, you should probably put it into your repertoire. And because I don't believe you, because people who don't like to admit that they don't know something, it's a weakness actually. Go ahead and admit it. I admit it all the time when I don't know things. But I don't want to have to deal with your weakness right now. I'm just going to help you. Theta, 90 minus theta, right? So opposite side, adjacent side, hypotenuse based on theta, correct? So sine of theta is based on theta, this would be the opposite side. Sorry, this would be the adjacent side. Want to make sure I at least get it right for theta. Opposite over hypotenuse, but cosine of 90 minus theta would be, this side would be the adjacent side to 90 minus theta. That would make that opposite over hypotenuse. Good? So do you understand that if I do the reverse of this and do sine of 90 minus theta, I'd get adjacent over hypotenuse, and cosine of theta would be adjacent over hypotenuse. Everybody sees that? So now we understand why that's true? All good. All good. All right. All of that basically for us to get this relationship, right? That is the result of doing the net force problem. But we can't solve that for mu because it's in terms of a force we don't know. The normal force in the wall. It's an inequality, so we know it's somewhere less than that, but we don't know what it is. So now we have to find a way to get an expression for the normal force from the wall in terms of the other things in our problem. I'm going to redraw the ladder for just a minute. This is to aid us with figuring out some of the directional stuff. Here's our ladder. It's experiencing the forces we just talked about. Normal force from the ground, frictional force from the ground, weight of the ladder, weight of the person, normal force from the wall. All good? Where do you want to put the pivot point? We don't know necessarily these forces. We know this one because it's the weight of the ladder and the person. So I'd say we do know that one, but we don't know either of those two. If we put the pivot point here, we could get the friction, sure, but we have 4 torques to deal with. If we put the pivot point here, we have 3 torques to deal with. But our goal is to get either this force or this force. So I think we put the pivot point to the left and eliminate those 2 torques, solve for the normal force in the wall, because that leaves us only 3 torques to work from. Is that good? We do it the other way, but I think it's more work. So I'm going to basically, I'm going to ignore that force and that force, get them out of the way so I don't have to see them. Whoa, I don't know what happened there. And put my pivot point right here. I know net torque equals 0. And there are 3 torques. There's the torque from the wall, there's the torque from the ladder, there's the torque from the person. For every torque, there is R, F, sine of the angle, and whether it is positive or negative. So we gotta evaluate each thing. Let's start with the wall. The torque arm length, L. The force, normal force from wall, sine theta. And what do you want to do here? Do you want into the board to be positive or out of the board to be positive? Into? All right. Into the board is positive. So let's go right hand rule this sucker. Pointer finger along the torque arm. My force from the wall is upwards. So that makes for a torque that is out of the board, trying to cause the ladder to go that way. Right? Trying to push the ladder off the wall. So that will be a negative torque based on your decision for positive and negative. Ready? Go on to the next one. Next one, the torque from the ladder. That occurs at L over 2, right? The center of the ladder. And it will be mg sine of 90 minus theta. See if it's positive or negative. Go back over here. Pointer finger. My finger's downwards in the direction of that force. My thumb is into the board, trying to get it to turn this way. Seems to me like that's going to be a positive torque. So I will assign it positive, and we know the person's going to be in the same direction, so I'm just going to make the positive there. It is a distance d from the pivot point, capital Mg times the sine of 90 minus theta. All of these have to sum to be equal to 0. All good? Let's go ahead and put it all together then. dmg cosine theta plus L over 2 mg cosine theta minus L and W sine theta equals 0. All right, again, looking at this equation, we were given everything in this equation except for the normal force from the wall. That's what we're trying to solve for. Because over here we have normal force from the wall is less than or equal to mu g times m plus m. Trying to find mu. If I want to preserve my inequality, I'd probably like to sub into my inequality. Ready to keep going? All right. Here's where the problem kind of leaves the realm of physics and goes into the sanctuary of algebra. I need to solve the right side for the normal force. So first I'll do is just on the other side, equal sign. That look good? There are some things I can factor out. Like I can factor out the g cosine theta. I'm not sure how useful that is, but I can. So if I do that, I get g cosine theta times dm plus L over 2 little m all equals L NW sine theta. So I can divide both sides by sine theta. Divide both sides by L. And that leaves me with normal force from the wall equals G over L cotangent theta times dm plus L over 2. Not pretty, but that's what we got. We're going to put it here. So you ready to do that part now? You're going to do some more rewriting than I am. I'm going to substitute it in there, but I'm going to do so by, well, I guess I'll do it this way. By saying less than or equal to mu p m plus. And we want to solve for mu. I will say that I can get rid of the g. I have a g on both sides. It's in every term. There's nothing pretty here. So I have cotangent theta over L times dm plus L over 2m, all divided by m plus m. Has to be less than or equal to. Nothing pretty about that at all. And nothing particularly outstanding either. The angle is clearly involved in determining how much friction you're going to need. And does cotangent increase as theta increases or decrease as theta decreases? Do you know? It does what cosine does, because cosine's on the top now. So it decreases, right? So as the angle gets smaller, it takes less friction. Does that make sense? I don't think so. But cotangent's kind of funky that way. Look at the way the cotangent curve looks. Look at the other stuff, though. D clearly has an effect, right? Right? D scales how big friction has to be because the person scales that one. It's a weighted average. As a person starts at the bottom of the ladder, as they climb up the ladder, M doesn't change, but the amount M impacts the necessary coefficient changes. Do you see that? But also, the length of the ladder seems to have an impact in the other direction. The length of the ladder gets bigger, although it shows up here, it also shows up here, right? If I put that through, it'll cancel out with the term for the mass of the ladder. It doesn't cancel out with the person. So a longer ladder takes less friction. Now, obviously, make everything bigger and you can get more normal force, therefore you can get more frictional force. Right, you see that in the denominator, but that also affects the numerator, so that impact is probably less than you think. But this is an odd relationship all around. It's not obvious what's happening here. It's very animated out there.